Hello, my dear students. Welcome back to the online lecture video series on electromagnetic theory by AVS Deepak. Till now, in our discussion of electromagnetic theory, we have discussed the concepts of coordinate systems, the concepts of electrostatics, and the concept of magnetostatics. In the current module, we will discuss Maxwell's, Poisson's, and Laplace equation for the static, electric, and magnetic fields. Out of these, you may remember that we have already discussed Maxwell's equations while we are discussing the concepts of electrostatics and magnetostatics separately. In this module, we would try to list the Maxwell's equations at one go. So, while we have discussed electrostatics, we have seen that static electric fields are created by charges at rest, and these electric fields are governed by two fundamental principles. The first of them is that electric field intensity is conservative. That is, circulation of electric field intensity over a closed path is always equal to 0. Please be minded that this is for static fields only. Okay, and the next equation is given to us by Gauss, that is the Gauss law, which states that the number of flux lines leaving any closed surface is equal to the charge enclosed by the surface. That is, the surface integral of electric flux density, closed surface integral, that is, closed surface integral of electric flux density is always equal to the charge enclosed by the surface. Now, for the static electric fields, these two are Maxwell's equation in integral form. In differential form, we can deduce them using the Stokes theorem and divergence theorem. Stokes theorem relates the closed path integral to an open surface integral as closed path integral of any vector field is equal to the open surface integral of curl of that vector field. But because this is equals to 0, this integral is also equals to 0. Therefore, which is universal for all the surfaces possible, del cross E bar should be equal to 0. We have already seen this discussion while we have seen electrostatics. Del cross E bar is equals to 0, and such E bar is called as irrotational vector. Similarly, divergence theorem relates the closed surface integral to the divergence of a vector field, which states that closed surface integral of any vector field is equal to the volume integral of divergence of the vector. So, using this principle, we have obtained that del dot d bar is equal to rho v. That is, divergence of electric flux density at any point is equal to the charge density at that point. So, the difference between integral form and the differential form is that in integral form, these equations discuss for a closed path and a closed surface, that is, a body or a region as a whole. Whereas in differential form, they discuss the electric field intensities and electric flux densities, the relation for a point. We discuss these, we define this curl and divergence for a point. So at any given point, the curl of electric field intensity is equal to 0, and at any given point, the divergence of electric flux density is equal to the charge density. So these are the Maxwell's equation for static electric fields in differential form. Now similarly, magnetostatics, while discussing magnetostatics, we have seen that magnetic fields are generated because of constant currents, that is charges moving with uniform velocity. And there are two fundamental principles which govern the magnetostatics. That is, the first one is that magnetic monopole does not exist. That is, number of magnetic poles on any body will always be an even number. That is, if there are n number of north poles, there will be n number of south poles in any volume. Therefore, the number of magnetic flux lines leaving any closed surface is equal to 0. This is because there are no magnetic monopoles. The second principle is the Ampere circuit law, which states that the circulation of magnetic field intensity over a closed path is equal to the current enclosed by that path. That is, integral of h bar dot dl bar is equals to I enclosed. Again, for static magnetic fields, these two are the Maxwell's equation in integral form. Applying divergence and curl respectively for both these equations, we would get del dot b bar is equal to 0, applying divergence to the first equation, and applying curl to the second equation, where I enclosed can also be written as integral of j bar dot ds bar, and this can also be written as surface integral of del cross h bar dot ds bar. Therefore, this is applicable for all the surfaces. Del cross h bar is equals to j bar. That is, curl of magnetic field intensity is equal to the the current density. The curl of magnetic field intensity is equal to the current density. This is the Maxwell's fourth equation. So there are four Maxwell's equations for static fields. Two of them are del dot b bar equals to 0 and del cross h bar equals to 0. So del cross h bar equals to j bar, and del cross e bar equals to 0 and del dot d bar equals to rho v. So these are the four Maxwell's equations for static. Next, we would discuss the Laplacian equations and the Poisson's equation. But before we discuss the Laplacian and Poisson's equation, we should discuss a special type of vector operator called as Laplacian operator. This Laplacian operator can be applied on both scalars and vectors. If we apply this on scalars, then the Laplacian of a scalar field will also be a scalar field. And the Laplacian of scalar field is obtained as divergence of gradient of a scalar field. That is del square of s. This is the representation of Laplacian operator. Laplacian operator is represented as del square. So del square of s is equal to del dot del s. The meaning is dot represents the divergence operation and del f represents the gradient operation. So the Laplacian operation is divergence of gradient of a scalar field. For vector fields, Laplacian of vector field will also be a vector, and its value is gradient of its divergence minus curl of its curl. That is, del square of v bar is equal to divergence of its gradient minus curl of its curl. So this is how you obtain the Laplacian of a vector. Now you may remember from our earlier Maxwell's equation, we have del bar dot d bar is equals to rho b. But we know that d bar can also be written as epsilon e bar. Therefore, I can write divergence of epsilon e bar equals to rho b. If I take epsilon outside, then I can write divergence of electric field intensity to be equal to the charge density divided by the permittivity. But as you know that static electric field is an irrotational vector, and all irrotational vectors can be expressed as gradient of some scalar fields, and such scalar field is minus V, where V is the electric potential, which is given by V equals to minus E bar dot dl bar. We have discussed that while we have discussed electric potential. So E bar can always be written as minus del B. So this equation, I can rewrite this to be del dot minus del V to be equals to rho B by epsilon. If I take negative outside, then I am getting minus del dot del V to be equals to rho V by epsilon, where this del dot del V is nothing but the Laplacian of scalar potential. So the Laplacian of scalar potential is equals to minus rho V by epsilon. This equation is called Poisson's equation for static electric fields, which is Poisson's equation for static electric. Similarly, in case of magnetic fields, we have del cross H bar equals to J bar. But we know that B equals to mu H bar. Therefore, if I write the curl of B bar, that would be equals to mu times J bar, where B bar is a solenoidal vector whose divergence is 0. Therefore, B bar can always be written as del dot A bar, where A bar is called as vector magnetic potential. We have seen that in the magnetostatics concept, vector magnetic potential A bar. So I can rewrite this to be del cross A bar. But the interesting thing about A bar is not unique. That is, you may add any gradient of scalar field to this, and if you calculate the curl of it, the answer would be curl of A bar plus curl of gradient of the scalar field, where we know that curl of gradient of the scalar field is always 0. Therefore, the answer would still be equals to B bar. Therefore, the magnetic vector potential is not unique. You can have multiple vector magnetic potentials. And this del cross A bar, if we observe the expression for the Laplacian of vector field, del square A bar is equal to the gradient of its divergence minus curl of curl. Therefore, I can write the curl of curl to be equal to the gradient of its divergence minus the Laplacian of A bar. And this is equal to mu J bar. Now, as I have already told you, this A bar is not unique. So, if I write this A bar prime to be equals to A bar plus gradient of some scalar field delta S bar, such that its divergence is equals to 0. Okay? How will its divergence be equals to 0? Because del dot A bar prime would be equals to del dot A bar plus del dot del S. Right? So, if this is to be equals to 0, that means del dot A bar would be equals to del square of S. So, if I write a scalar field like this, which is quite possible, whose Laplacian is equals to the divergence of the magnetic potential, then for the updated vector magnetic potential, the gradient of it would be equals to 0. Therefore, when this term reduces to 0, I am left with the Laplacian of A prime. So, the Laplacian of A prime would be equal to minus mu J bar. This is called as the Poisson equation for static magnetic fields. The Poisson's equation for static electric fields says that the Laplacian of electric potential is equals to minus rho v by epsilon for charge-free region, that is when the charge density is equals to 0, the Laplacian of electric potential is equals to 0. This is called as the Laplacian equation for static electric fields. This is defined by charge-free region. Similarly, the Laplacian of vector magnetic potential is equals to minus mu J bar in a current-free region, that is J bar is equals to 0, del square A bar is equals to 0. This is called as the Laplace equation for static magnetic. That is it. That is the discussion in the current module. In this module, we have discussed the Maxwell's equation, Poisson's equation, and Laplace for static electric fields. What will be the case when the electric fields and magnetic fields are no longer static but are time varying? You would see in the next. Thank you. For any comments, please ask in the comment section.